Chapter 4, Section 4, talk about the natural logarithm function. So let's recall exponential function. Right? If we have exponential function, let's see. Let's use the Euler number, e to the x. This is from the previous video. So e to the x equals f of x. We can rewrite this. We can rewrite this as x equals to log base e, which is ln, f of x. I'm going to use the example. Let's first just to see with a normal or number, right? Let's say 2 raised by 3 equals to 8. So I can rewrite this as a 3, because my emphasis is on 3 now, equals to log base 2 of 8. Just a different way of writing this equation, right? Because if I have 2 raised by x equals to, let's say 32, I want to solve for x, so I can write it as x equals to log base 2 of 32. You see, I read 2 is at the foot of g. So 2 is the base. 2 is the base in exponential form. 2 is the base in logarithmic form. Just a way of looking at the beginning, but yeah, whenever you get confused with the meaning of log, you think about the log is the exponent of the base. Okay. So if we write as a 2, because this is an x, 2 raised by x equals 32, then 2 raised by log base 2 of 32 equals to 32. So log means the base, the exponent of the base. Okay, so right, we continue e, right? We continue e to the x equals to some number. Let's say equals 32. So I want to solve for x. I can rewrite as log base e of 32. But then log base e, we simplify to be ln. ln, so natural log. So that's this, natural logarithm. So I just have to, I don't need to write e anymore. I don't have to write L or GE. Instead, I write ln 32. All right, so we can switch exponential equation into logarithmic equation. So that means that these two has a very close relationship. Right? If we make a function, those two functions are called inverse with each other. Inverse with each other. So the graph of them are symmetric with this y equals the x line. So if I graph 2 raised by x, let's say this is 1, right? 2 raised by x, exponential form, something like this. Then the logarithmic is symmetric with y equals the x line, goes like that. Okay. So inverse functions, the graph of them are symmetric with y equals to x line. Inverse means if I have function going from this to this, that's a function, that's f. Then the inverse is the opposite. We write as f raised by -1 of x. Let's put this way, right? So function sends the input from here to here, output, but the inverse sends this one, the output, to this input. So that's why you see here, if we have 0.5 comma 7, and the inverse function would have 7 comma 5, because we're switching x and y. Think about this as x set, this is a y set. Now we're basically sending this one y to be x, right? So this is f of x to be y. F takes x to be y. Then the inverse of f takes y to be x. So that's why you see the position are switched. So those 2 points are symmetric with y equals x line. So this is e to the x graph. Then we can graph ln e. Let's take a look at this. So this y equals x line cuts the first quadrant and third quadrant into half, right? So which means every point, the x value and the y value are the same. So e to the x exponential growth, increasing function, right? ln x is inverse, also increasing function, but it goes this way. So those 2 graphs are symmetric with y equals x. So there are some properties of logs. So ln1 equals 0. Why? ln1 equals to 0. We can rewrite this as base is e, because ln tells us the base is e raised by 0 equals to 1. So anything raised by 0 equals 1. ln e equals 1. Well, ln e equals 1. Why? Because e raised by 1 equals to e. Always remember, log means these guys are exponents of the base. And then 3, ln e to the x equals x, right? Because ln e to the x equals to x. Because ln base e, because ln e to the x. So what can we write? So let's see, first we write this equals to y, right? So we can rewrite this equation into e raised by y equals to e raised by x. So base is the same, the forces, the exponent to be same. So that's why y equals to x. So ln e to the x equals x. Or we can remember this. We can pull this exponent of the value up front. So which means ln e to the x I can pull up front of ln, right? The same as x ln e. Well, what's ln e? ln e equals to 1. Right? X times 1 equals x. Okay, so number 4, e to the ln x equals x. So e to the ln x, let's see first, let's equal to y. Then we can rewrite this equation, right? We can rewrite this equation by taking ln e, ln y. So then this ln x is the exponent of e, we can pull up front. So ln x, ln e equals to ln y. Well, ln e is just 1. So ln x equals to ln y. So that's why y equals to x. So that's why e raised by ln x equals to x. Right? So those are some properties, special properties for logs. So make sure you can remember those by heart. Okay, so let's simplify these expressions. Right. So the first one is e raised by ln 4 plus ln 5. So there are other properties. So something called a product rule for exponents. Let's see where does this come from. If I have 2 raised by 3 times 2 raised by 4, remember we can add those 2 exponents, right? I get 2 raised by 7. Right? Remember ln 4, each one is exponent. So that means we can split this as e ln 4 times e ln 5. Well, remember e raised by ln x equals to x. Right? So that means this one equals to 4 times 5, which is 20. But let's see this one. This is e ln 4 times e raised by negative ln 3. Remember, e raised by negative. That means it should go to the denominator. E ln 4 divided by e raised by ln 3. Well, e ln 4 equals 4. E ln 3, e raised by ln 3 equals 3. So that's 4 over 3. And for this one, c will be e ln 3 times e 2 times ln 4. Remember, this 2 can be pulled to the up to be an exponent of 4. So it's e ln 3 times e raised by ln 4 squared, which is 16. Well, that's 3 times 16, which is 48. Lastly, we have ln. We can write as e raised by negative 2. Okay. Then we can pull this negative 2 up front, ln e. Well, ln e is 1. So that's why this equals to negative 2. So all this being simplified by the properties. So can use the property to solve equations. Sometimes if we're given exponential equation, we want to change to logarithm equation. Well, let's see this one. So first we want to divide it by 5 on both sides, right? So when we divide 4 by 5, we get 0.8. So what do? Now we want to change to be ln. We want to take ln on both sides. We want to change to be logarithmic, right? Because why? Because once we take this as ln logarithmic, the exponent of e comes up front. So I have x minus 3 times ln e, while ln e equals 1. Right. So then x minus 3 equals ln 0.8. So x equals 3 plus ln 0.8. We use a calculator, that's about 2.777. Okay, that's we use logarithmic to solve for exponential equations. Let's see this one. This is logarithmic equation. So we have 2 ln x plus 7 equals to 0. That means ln x should be a negative number, right? So, oh, we have here. So let's move positive 7 to the other side, become negative 7. So 2 ln x equals negative 7. Then we divide by 2 on both sides. Ln x equals negative 3.5. Then we can, so this is the same, we could do this. Instead of saying we raise both by e, we could say, I can rewrite this as e raised by negative 3.5 equals the x, right? Remember, log x equals to log base e of x. If this equals a negative 3.5, the equivalent expression is the base e raised by this exponent equals to the value. So we don't have to take this step. Okay. So we get in one shot x equals to e raised by negative 3.5. Just remember before I mentioned this, 2 raised by 3 equals to 8. I can write it as a 3 equals to log base 2 of 8. If I have e raised by 3 equals to a number, let's say a, I can rewrite as 3 equals ln of 8. So e disappeared because ln represents log base e. This is saying if we have b raised by x equals e raised by kx, and then k can be written as ln b. So this is exponential function with base 2, a logarithmic function with base 2, they're symmetric because they're inverse with each other. This is log base 10. Okay, let's see this example. So seeing the investment portfolio with value in $1,000 given by this, this function, right? T is the number of years. And so we want to find the value of T where this minimum occurs. So the graph, so which means remember the minimum, and if it's a minimum, something like this is on the bottom. So what is the property of the minimum point? The slope of the tangent line equals 0, which means the derivative happens at this value of t equals 0. So we want to use this property. So first, we need to take a derivative of this. When we take a derivative, we have 15 times 0.02. That's 0.3. Then we multiply by e. Remember, the e term always survives in the derivative. E raised by 0.02t, then minus 0.06 times 10, this is 0.6. Then the e term, e raised by negative 0.06t. So we need to set this one to be 0. So once we set this one to be 0, we can solve. We can factor out, let me just follow the textbook. So we have, so then we can pull this negative term to the other side. So I have 0.3 e to the 0.02t equals 0.6 e to this one. And now this is saying, let's just get rid of the 0.06t by multiplying e raised by, because e raised by 0.06t, multiply this term on both sides. So then this side we get an e raised by 0, which is 1. So we only have 0.6 left. That's how we combine those two terms. Right? We want to be able to combine those two terms. Then we divide by 0.3 on both sides. So we get 0.6 divided by 0.3, which will get 2. Then we take ln on both sides. Take ln on both sides. Then the exponent of e comes down. Then ln e is equals to 1. So this side we have ln 2. Then we divide by 0.08 on both sides. So ln 2 divided by 0.08, we can use calculator. That's about 8.66. So about 9 years it takes that to happen. Okay, so that's how we use, solve. The idea is the same, right? Find the minimum, which means the derivative at the point equals 0. We'll find the derivative of the function, we set to 0, then we solve for the variable. But in this case, the variable is in the exponent. So we'll have to use a logarithmic form to solve it. All right, that's 4.4. Let's see 4.5. So this property is very useful. E raised by ln x equals x. All right, so a couple of things we need to remember. ln 1, natural log of 1 equals 0. ln e equals to 1. ln e raised by x equals to x, right? Or, and this one also, e raised by ln x equals to x. Okay, these properties, we need to remember them. So when we take derivative of this, so when we differentiate e raised by ln x, then what do we get? We get e raised by ln x, then derivative of the exponents. Remember, we have e raised by g of x term. When we take derivative of this, we get e times g of x, then multiply by g prime of x. So I have to take derivative of the exponent. Then, so x equals the derivative of ln x. Then we have this one, right? We have e raised by ln x equals to x. E raised by ln x equals to x. So that's why this e raised by ln x becomes x. So derivative of e ln x is x times derivative of ln x. Well, then we differentiate ln x. Well, derivative of x is equals to 1. So which means x times derivative of ln x equals to 1. Right? Because of this, because of the equation e raised by ln x equals to x. And then, so derivative have to be the same. So the derivative of this one has to be derivative of this one. Well, what is the derivative of this one? That's 1. So that's why this becomes 1. Right? Then we have to divide by, so derivative divided by x on both sides. So derivative of ln x equals to 1 over x. Well, let me use shorthand. So derivative of ln x equals to 1 over x. That's very interesting, right? Derivative of a logarithmic function, the rate of change of a logarithmic function becomes a rational function. And they'll keep taking second derivative. That's derivative of 1 over x. That's going to be negative 1 over x squared, which we know this family already, rational function family. So this is a graph of ln x. Now let's differentiate those ones. So we have 2 layers, right? We have a first layer, something with the input raised by 5. Now the inside layer is take the ln of the x. So when we take derivative, chain rule involved. So we take 5 down, then ln x raised by 5 minus 1, which is 4. Then we take derivative of ln x, which is 1 over x. Right, so we can rewrite that as 5 ln x raised by 4 divided by x. And of course, x cannot be 0. Let's see this one. This one we see product. Right, so the first one is by chain rule. Right, you see we have chain rule. We take care of the exponent 5, then we take care of the derivative of inside. For B, I see product of 2 functions. I see x times ln x. So I take a derivative, I'm going to use product rule. Product rule introduce a plus sign. I take derivative of the first one, which is x, which is 1, right? Times second one, which is ln x. Then I take a derivative of the second one, multiplied by the first one, while 1 ln x derivative is 1 over x. 1 times ln x is ln x. Then x times 1 over x is just 1. So I get ln x plus 1 as a derivative. This is saying inside the ln could be a long expression. Right, let's see what have this. Maybe we're given a function as ln of x squared plus 2x plus 3, something like that. So when we take a derivative of f, first layer is ln. We take a derivative with ln, that's this part. Right? So inside this is g of x. So I have 1 over, remember ln x is 1 over x derivative. So 1 over this gx, which is x squared plus 2x plus 3. Then we have to take a derivative of the inside, take a derivative of g. In this case, just 2x plus 2. Right? And this 2x plus 2, I can write in the numerator, 2x plus 2 divided by x squared plus 2x plus 3. Right? So this is also compositional function. So by chain rule, so I have to take a derivative of outside layer, then take a derivative of the inside layer. Let's see these examples. We want to differentiate them. So this one, y prime equals to first 1 over x, 1 over 2x plus 1. Then derivative of the value, which is 2. 1 times 2, which is 2. So 2 over 2x plus 1. Similarly, y prime for the b equals 1 over 4x squared minus 2x plus 9. Then multiply by the derivative of inside. Right? We see that's 2 times 4, 8x. Then minus ax minus 2. Right? Derivative of 9 is 0. Well, C is a little bit complicated. Right? First layer, we have 1 over x times e raised by x. Now, we have to multiply by product rule called a sum. Right? Because we see this is a product of two functions. So derivative of x is 1, so I have 1 times e raised by x. Then x times the derivative of e to the x is still itself, e to the x. Then we simplify, we get e raised by x plus x times e raised by x divided by x times e raised by x. Well, this can be simplified further because we see every term has e raised by x, right? So we can just divide it by that, e raised by x, 1 plus x divided by x times e to x. Now you see the common factor in the numerator, in the denominator becomes 1. Something divides itself, becomes 1. So that's 1 plus x divided by x. Or 1 over x plus 1. So once we see the product, we have to apply product rule. Example 3 is saying the function f of x equals ln x divided by x has a relative extreme point for some x greater than 0. Find the point and determine whether it's relative maximum or relative minimum. Okay, remember either one, the function derivative has to be 0. Because the slope of the tangent line for maximum, slope of the tangent line for minimum is 0. Okay, slope is 0, it's a horizontal line. It's a constant function, will never change. So first we need to take derivative of this. So f of x equals to ln x multiplied by x. I like to write x up front. oh, x raised by -1 divided by x, right? I can write that as x raised by -1. Then equals to ln x multiplied by x raised by -1. Then let's take derivative. Derivative of ln x is 1 over x. Then times 1 over x, right? Because x raised by -1 is 1 over x. Then plus negative, because we're taking derivative of x raised by -1 now. We know that's 1 over x squared. Then negative 1 over x squared. Then multiply by the first one, ln x. So I have 1 over x squared minus, actually, we can factor out. We have, oh, what I'm writing. What I'm writing. I already pull out the x squared, right? 1 over x squared. That just becomes 1 minus ln x. So now we want to set this one to be 0. Set this one to be 0. Multiply x squared on both sides. We have 1 minus ln x, or 0 times anything will be 0. So ln x equals to 1, which means x equals to e. Right? This exactly means e raised by 1 equals to x. So now we have this. So the inflection, not inflection, the critical point, critical number is e, x equals to e. So we can split into negative infinity up to e, and the e up to positive infinity, 2 intervals. Right? 2 intervals. Let's see, this is the number e. E split real number system into this lower half, this upper half. Because we need to check if this point is maximum or minimum. Right? If the function increases or decreases, how do we do that? How do we check f of x increase in the interval or f of x decrease in the interval? By substitute e into the derivative function to see if it's positive. If it's a positive value, that means the original function increases. If it's a negative value, it means the original function decreases. So it's just going to do that. So e is bigger than 0. So 0 is in this interval. Well, we could just evaluate 0. Oh, we cannot evaluate 0. Why? Because you see x squared in the denominator, x can never be 0. But 1 is smaller than 2.71 something. Okay? So let's use 1. Well, so let's use 1. So f prime of 1 equals to, in the end, what do we get? We get a 1 minus, ln x divided by x squared, right? We get a 1 minus ln 1 divided by 1 squared. Remember what's ln 1? ln 1 is 0. Divided 1 squared divided by 1. So 1 divided by 1 is just 1. So we get this 1, 1. Well, 1 is a positive number. That means the original function, let's see, this is point. Right? This point, the x value is e. The y value is f of e. And on the left-hand side of this point, this value e, the function increases like this. Then after this, it has to be decreases. So that's how we know this one is a maximum. It's not minimum, right? The function increases up to this point, they turn to the other way. You could follow the textbook to find a second derivative, then go some analysis from there, all right? Because second derivative, only when we talk about concave up, concave down to find inflection points, we need it. Otherwise, we don't really need it. So derivative of absolute value. Derivative of absolute value functions, we take ln. So this is just a process. Right? Remember the graph of ln x. The graph happens on the right-hand side of x-axis. So which means the domain of ln function has to be positive. If x is given as a negative, then we'll have this kind of graph. We'll have to negate the negative. But in either case, so we can prove going through these calculations, derivative of ln of absolute value of x equals to 1 over x. Right? So we can still use that. So derivative of ln absolute value of x equals to 1 over x. Okay, that's 4.5. Talk about a natural log, derivative of a natural log function. 4.6 talk about some properties of natural log functions. So I have those properties. If we have a ln of one term times another term, we can split into two logs, right? So log of product can be split as a sum of two logs. Log of division, right? In this case, it is 1 over x because this is ln1 minus this. Well, ln1 is 0. So in general, if we have ln x divided by y is a quotient in the value, we can split into ln of the numerator, subtract ln of the denominator. Or we can remember, inside ln, the denominator comes off as negative. Ln x raised by b, this b comes up front, becomes coefficient. So those are some examples. If we have ln x times y, we can verify, we can prove, right? Remember, x can be written as e to the ln x, y can be written as e ln y. Then we can write as e ln x plus ln y, right? Then this is, we can rewrite as e, remember that comes from this. E to the a plus b equals e to the a times e to the b. Then we can pull this exponent up front. Then we just left with ln e. Well, ln e is just 1. 1 times ln x plus ln y is still ln x plus ln y. So this one, the second one proves ln 1 over x equals negative ln x. We can change, again, we can change x to be e to the ln x, right? That's a negative. Or even simpler, we can do ln x raised by -1, or then the -1 comes in the front. So that becomes negative ln x. Number 3 is similar. Okay. We have ln x times ln x divided by y can be written as ln x times y raised by -1. Right? That can be split as ln x plus ln y raised by -1. Well, -1 can come up front. That becomes ln x plus negative ln y. Well, plus minus becomes minus. So if we have ln, like a very complicated, we have b, a, b, c, let's see, d, e. So when we split, this is ln d. In the numerator, we split into positive terms. In the denominator, we split into negative terms. All right, just a rule of thumb. Similarly, 4. So this one is saying, write ln5 plus 2 ln3 as a single log form. So this is opposite, right? And first, we want to pose the 2 to be exponent of 3. We have ln5 plus ln3 squared, which is 9. Then this just becomes ln of 5 times 3 squared. It becomes ln 45. So this is, let's see this one. We have a half of ln of 4t. Remember half? Half means we can pull up from here. Up from half can be pulled as exponent. Then something raised by half, that means a square root, right? Square root of 4t ln. Then minus this one. That means that becomes in the denominator t squared plus 1. So just 1 ln of 1 term. Right? Square root of 4t, then divided by, because this is minus, divided by, so t squared plus 1 happens in the denominator. A square root of 4 is 2, so we can write as 2 square root of t. This one have ln 3, ln x, ln y minus. So if it's a plus, I just multiply them. I have x times 3 times y. If it's a minus, I just divide them. So simplify, so this to be 3xy divided by 5. Okay, this one we want to differentiate. We have one product, another product, another, we have 3 products. We have 3 products. So what do we do? So first we want to split this function. Remember, product of 1 log, we can split into product, we can split into addition of 3 logs, right? We have ln x plus ln x plus 1 plus ln x plus 2. Because here we have 3 products. We can split as a sum of 3 logs. Each one takes logs. Then we differentiate. Right? When we differentiate, this one give us 1 over x, this one give us 1 over x plus 1. The derivative of x plus 1 just 1. Doesn't change anything. The same thing for this 1 over x plus 2. That's it. So that's the derivative. You see how important to use the properties of logs? So this one saying, differentiate this function, use logs, which means take a logarithmic on both sides, right? Once we take a logarithm on both sides, we split into log first one, log second one, log of the third one. Then we differentiate this. We differentiate both sides. Differentiate this side. Oops. So we differentiate this side. What do we get? Remember, ln of something equals 1 over something, then something derivative, right? So that is g prime of x equals g of x. Then the derivative of this one is 1 over x squared plus 1 multiplied by the derivative of x squared plus 1, which is 2x. And derivative of this one is 1 over x cubed minus 3. Then multiply by derivative of x cubed minus 3, which is 3x squared. And then this one, 1 over 2x plus 5. Then multiply derivative of 2x plus 5, which is 2. So we have this. Then what is g prime? G prime just equals to both sides multiplied by g. Right? And g is this multiplied by g. Then we can simplify this. So this becomes 2x, because for the first one, this was cancelled, right? X cubed minus 3, 2x plus 5. Then the second term, x squared, x squared plus 1. But the x cubed minus 3 is simplified, cancelled, 12 plus 5. Then plus 2 times x squared plus 1 times x cubed minus 3, right? And this cancelled. So this one is saying, if we have f of x equals x raised by r, we take our n on both sides, right? Then this r can be moved up front. Right? This makes things very convenient to calculate. Then we differentiate both sides. Our n f of x, just f prime of x divided by f of x. Then derivative of the other side, just r times 1 over x, because derivative of ln x is 1 over x. Then we can rewrite the differentiation, the derivative of f as f prime of x equals r times 1 over x times f of x. Well, r times x raised by r times 1 over x times x raised by r, let's just r times x raised by r minus 1. What do we see? We see the power rule here, right? Okay, that's to differentiate logarithm functions. All right, that's chapter 4.